Well, thank you for the very nice introduction. I want to acknowledge appreciation for all the folks here, in particular Professor Wong, who organized this event, and it's been delightful. I've met a lot of good students, particularly a young lady who's helped me out so much, and I appreciate it very much. I'm happy to be able to be here today and tell you a little bit about some of the things that we've been doing. You are all perfectly well aware that the development of polymer science, which began about the middle of the last century, has had tremendous impact on society as a whole. Every single one of you has devices that you couldn't have had if it had not been for polymer science. So there have been tremendous advances. But for most applications, they must be flame retardant. Oops. Okay. If we simply look at this simple diagram, we can see where the opportunities lie for doing flame retardancy. If you heat any polymer to a sufficiently high temperature, almost any polymer to a sufficiently high temperature, it begins to degrade thermally. And that thermal degradation generates small molecule units which get to the gas phase, mix with oxygen, and if the temperature is sufficiently high, ignition temperature or above, then combustion may be initiated. Combustion is a series of exothermic radical reactions, and heat and light are produced. We see the heat as flame. If combustion is not complete, we may also get some particulates that we see as smoke. The heat from the combustion process can feed back to the polymer. That enhances the rate of degradation, enhances the rate of fuel formation, and enhances the combustion. Thank you. And so there are two opportunities where we can inhibit this process. The first is in the polymer phase, in the degrading polymer. That is, we can inhibit pyrolysis, or we can attack the combustion process itself, and so inhibit the reactions, the important reactions that occur in the gas phase. Now, as you know, over the years there have been many materials used as flame retardants. Early on, particularly metal oxides and various other things have been used. One of the problems with these materials is that they generally function by liberating inert fragments to the gas phase to dilute the fuel load. And so to get effective flame retardancy, a large amount is required, to the point that often the polymer integrity is impaired. And so these materials are often used in polymers for which integrity is not important, such as cable coating or paper coating. In the main, the effective flame retardants have been organic, and there have been two classes. First, organo-halogen, and then organophosphorus. There's some other things that sometimes get used, particularly organo-nitrogen compounds and a few organosulfur compounds. Typically, these are not primary flame retardants. They function in cooperation with the primary flame retardant. For example, organo-nitrogen compounds typically relate ammonia and other inert fragments to the gas phase to dilute the fuel load. So really, there are only two classes that one has to be generally concerned about. The most effective were the multiple brominated aerial ethers. Prior to that, organo-halogen materials, things like the chlorine plus, were prominent, but they aren't as effective because they degrade at a temperature beneath the temperature at which and most polymers degrade. So the aryl ethers have been very common. Diphenyl ether is a byproduct of phenol production, and so it's readily available, very low cost, and it can be readily brominated. The action of these materials is promoted by antimony oxide. Antimony oxide is not a synergist. It's not a flame retardant. It's a precursor to a flame retardant. In a degrading polymer matrix in which the flame retardant, the brominated material, is degrading, it's converted to antimony tribromide or oxybromides, which are volatile, get into the gas phase, and inhibit the radical reactions. And so the bromine that's present in the flame retardant is utilized more effectively. But the processes are not related. They're in parallel. The antimony oxide is toxic, particularly as a powder, and so there are many replacements being tried for this material. A problem is that many salts, many metal salts, will form trihalides or form halides in the matrix, but they're not sufficiently volatile to be effective. But in some cases, even iron chloride works. It takes more of it, and of course you have to put up with the color. So it has to be a particular application. But there are companies, there's one in the US, R.J. Marshall, which sells a variety of alternatives to antimony oxide, and they will work for some applications. One of the problems with the brominated aryl ethers is that they are persistent. They migrate from the polymer matrix, particularly if an item is discarded in landfill. And they bioaccumulate. And they get up through the food chain, and they may be toxic to human health. They have a very bad image these days, and so increasingly they're being removed, being replaced by other materials. These are some of the prominent ones. As I mentioned, the brominated diphenyl ethers, particularly decabromo diphenyl ether, been very popular. It's probably the most widely used at one time. Hexabromocyclododecane undergoes decomposition at a much lower temperature, but has been very effective for flame retarding polystyrene, particularly foam polystyrene. But it's no longer used for that purpose. What is replaced it in many applications is this oligomeric material. You can see that this is a copolymer of butadiene and styrene, and simply brominated. This was developed by Bruce King at Dow Chemical. It is now sold by most of the major flame retardant companies. So one approach to delivering on the leaching problem with the migration problem is to use oligomeric materials. One has to be careful that the molecular weight is not sufficiently great that compatibility with the matrix is lost. So that's a concern in using these kind of materials. The focus on organophosphorus flame retardants is increasing simply because of the need for newer materials. These have most commonly been phosphorus esters. The earliest ones were simple phosphates, but more and more we're seeing phosphonates and phosphonites. A difference is that phosphates undergo thermal decomposition at very low temperature, around 250 degrees, to eliminate a phosphorus acid. Whereas the compounds that are less highly oxygenated at phosphorus tend to generate gas phase active species. So phosphates are usually solid phase active. They decompose to generate phosphorus acids, promote cation cross-linking, and char formation. So a char layer at the surface of the degrading polymer inhibits the heat feedback. It's a thermal insulation barrier, and that slows down the pyrolysis and decreases the amount of fuel that's getting to the combustion zone, and so limits the combustion. For the phosphorus compounds which contain a lesser amount of oxygen at phosphorus, they often undergo decomposition to liberate, in principle, the PO radical. Lots of other things have been implicated, but the PO radical is the only one which has been rigorously established as a gas phase flame retardant. The most common compound is DOPO, as you all know. And there's a great variety of compounds now which contain DOPO. There are other things, the phosphoramidates and some sulfur-containing compounds, but they're much a lesser impact. So, if you want to make new flame retardants, what are the considerations? First of all, you want them to be highly effective. You'd like them to be just a drop-in replacement, if possible. So you want to start with readily available starting materials. You want them to be low in cost, and you want to be able to convert them to something useful using simple chemistry. If the chemistry is too complex, industry is not interested. They want fairly straightforward things, and you want non-migrating. And you get that two ways. One is if they're reactive and can be covalently bound, or if you use oligomeric materials, then you can blend them in, get a blend which the flame retardant doesn't migrate. If it gets out, you want it to biodegrade to innocuous products. So something that organisms in the soil or the water can assimilate and like to eat. So non-persistent in the environment. Where do you get those? You get them from a renewable biosource. And here are a few things that we have used. There have been others used by other people to make these materials. The first, tartaric acid. Tartaric acid is a byproduct of the wine industry, and so every year there are huge volumes generated. Some of it gets used, but most of it goes waste. So readily available. Chitosan is a biomaterial from the fisheries industry. Most shellfish have a structure of chitin, and that's just the acetylated chitosan. So lots of chitosan available as a reactive amino group, so you do lots of things with it. Plant-based phenolics. These are crop byproducts, particularly of grains. So again, a byproduct that's readily available. Here's one that I think has a lot of potential. We'll talk about that in a little bit. But the glycerol adipic acid is hyperbranched polyester. Using new technology that's recently developed, you can make these materials with any desired molecular weight, with a well-defined structure, and with a single in-group. Many people have tried in the past to do this, but they did it by experimentation, and so they ended up with a polymer, and maybe that didn't gel during polymerization, but it had two in-groups. There were carboxyl and hydroxyl, and on storage, it would gel. So we're not useful. But with new technology, you can get around that problem. The bis-hydroxymethyl furan is a starch derivative, and of course, isosorbide. Isosorbide is a nice derivative. It's been a workhorse. not only for making polymer additives, but making polymers that are interesting. Here's an example of tartaric acid. It's this structure. You see it has 2 hydroxyls, 2 carboxyls, and so it can be readily converted to a variety of materials. And this is just this is a vineyard in the state of Michigan, in which I live in the U.S. It's the 3rd largest wine producing state in the nation. And over here is the way you enjoy it. But so there are lots of tartaric acid available. Some of it's used in baking powder. Some of it's used in carbonated drinks to provide a tart taste. But huge mounds of it go to waste every year, so it's readily available. And a simple example shown here to make phosphorus esters at the hydroxyls, and then you can do a variety of things. You can saponify, you get this diacid, or you can make directly a oligomer using this substituted hydroxyquinone. So lots of flexibility there, a very inexpensive starting material. This is chitosan, and you see that you can make a variety of phosphorus derivatives. This one is the dopo derivative. It's a very nice flame retardant. And of course, you can select the molecular weight of chitosan that you would like. These are the plant-based phenolics. The one that's most available is gallic acid. It's a trihydroxy benzoic acid, so lots of functionality to functionalize. It's found in many plants and has been known for a long time because of biological activity. But even in the fall, when the trees change color and the leaves fall on the ground, if you grind those leaves up, you get lots of gallic acid. So it's widely available. The 3,5-dihydroxybenzoic acid is found in several plants, but in particular buckwheat. Buckwheat used to be grown widely, but not so much anymore. It's been surpassed by wheat. But buckwheat is used in the southeast of the U.S. for pancakes and in Japan for noodles. But at any rate, there's lots of this byproduct available. And there's just a look at how this can be done. First, convert carboxylic acid to the analyte for a couple reasons. That gets rid of its reactivity, introduces a nitrogen, introduces more aromaticity, but then you convert the hydroxyls to a variety of phosphorus esters. Similar with the dihydroxybenzoic acid, except we use the methyl ester as opposed to the analyte, but same procedure. And you can make a series of derivatives that have very, very good flame retardancy. This I mentioned. These are the hyperbranched polyesters from glycerol and adipic acid. Glycerol, as you probably know, is a byproduct of biodiesel formation. So there's lots of it available. And adipic acid is a natural acid, which is, again, inexpensive. And using a new approach, you can make these things with defined molecular weight. So select the molecular weight you want. Make sure you get good compatibility with a polymer. You get defined structure, so the branching is defined, and you get a single in-group functionality. In this case, the hydroxyls are shown, but you could make it with carboxyl as the in-group, and that gives you lots of opportunity to convert to phosphorus compounds. And so you can control not only molecular weight, but the level of oxygenation of phosphorus depending on what you use for esterification. Isosorbide is shown here. It comes from starch. You simply hydrolyze starch to get glucose, and then hydrogenate to generate sorbitol, and double dehydration gives you isosorbide. And there are now two companies that make this commercially available in polymer grade. So it's readily available, and there are lots of things you can do to it. You go through a fairly long procedure to get phosphorus esters, do direct formation of phosphorus esters. You can make the bisacrylate and then do Michael addition of phosphite to get something with phosphorus carbon bonds. And then you can make reactive derivatives for copolymerization to put the flame retardant into the main chain. And in our case, we've looked at low loadings, enough of the derivative to give us 1 to 2% phosphorus, and we've gotten very good flame retardants with that. And we use the standard small laboratory tests to examine initial flammability. And here's a series of the first set. You start with, whoop, come back here. Start with isosorbide, esterify with undecanoic acid, which you get from pyrolysis of castor oil. And that gives you terminal double bonds. If you do thiolene reaction with 2-hydroxyethane thiol, that generates hydroxyls at the terminal positions, which then you can make esters and get active species. And this is for the dopo derivative. It just gives you the reduction in peak heat release rate, and you can see that we get about 40% with 1% phosphorus. So it's an effective flame retardant. Now you can make the esters directly. The advantage of that is that you get more phosphorus per volume. And you can see again, you can make a variety of materials. And again, you see quite good reduction in peak heat release rate with 1% and then 2% phosphorus. And as I mentioned, you can first esterify with acrylyl chloride, and that generates the corresponding acrylate. And then you do Michael addition of phosphite, and you get a compound which contains a phosphorus carbon bond. These are much more stable than the previous ones we just looked at. In fact, when they undergo thermal degradation, they eliminate from the 5-membered ring. So initially you get a double bond here, double bond there. This is volatile, but it can be trapped and identified. That leaves you a carboxylic acid containing the phosphorus moiety, which doesn't degrade until higher temperature. That means that, for example, we look at this compound, the dopo derivative, degrades about 330 degrees C, which means that it can be used with polymers which process at a higher temperature, such as the polyamides. So it's a very nice material. And this is just a reflection of what you get. You notice that as you increase phosphorus loading, peak heat release rate goes down, the LOI goes up, and at 2% phosphorus you get a V0 rating in UL94. Now, you can, as I mentioned, make materials which are reactive. Note that in isosorbide, the two hydroxyls are not equivalent. One is exo, one is endo with respect to the rings both like this. One is over there, one is over here. And so they have different reactivities, which means that you can make phosphorus derivatives at either position. Then you can convert these to acrylates. Now you have an acrylate monomer, which has an active phosphorus compound. Oops. Okay, and this is just one simple example, copolymerization of styrene. As you know, styrene is rather difficult to flame retard, but if you make this copolymer, in which you get in about 7 mole percent of the comonomer, so not much, you get a very nice polymer that has very interesting flammability properties. You see that the TG is diminished a bit as we increase the loading of the comonomer, but not by a lot, not enough to cause any great difficulty in use. The thermal stability is not hugely impacted, so that it can be used in most of the applications to which styrene is used. But here's the big news. With 1% loading of the comonomer, we get a 50% reduction in the peak heat release rate. So tremendously effective in this particular application. Isosorbide is a very versatile material. It is readily available from starch. It can be converted to a variety of phosphorus derivatives, which function well as flame retardants. Can be converted to monophosphate monoacrylates and probably other things. We just haven't done that. To give you reactive flame retardants. And the most prominent is this one. You get a 50% reduction in peak heat release rate. So there are a variety of either biomaterials or bio-based materials. The bio-based materials are better for this approach. Biomaterials such as chitosan or castor oil, they come directly from the plant, but their composition varies from batch to batch. And that's a difficulty if you're trying to make things. Whereas bio-based materials, things like isosorbide, are always the same. You get pure material. Isosorbide materials, there are a lot of versatility in doing this. And so particularly one from DOPO, degrades thermally at a fairly high temperature, and so can be used with those polymers that process at high temperature. The one that has the best potential is the derivatives of the glycerol adipic acid hyperbranched polyesters. You can make variable molecular weight, so variable size. You can get variable levels of oxidation of phosphorus, and you get things that are compatible with a wide range of polymers. So they have great potential. I think the future, flame retardants are either going to be reactive or oligomeric. We somehow have to get around, one, the migration from the polymer matrix, and the fact that having the additive may contribute to flammability. So I just want to acknowledge some of the people who provided support. We couldn't have done this without some support. Chemtura did a lot of provided money for a lot of the isosorbide work. ICLIP provided diphenyl chlorophosphate. 2,5-bis-hydroxymethyl furan was provided by Penacam. And of course, DGEBA, which was the matrix for most of the examination, was provided by the Dow Chemical Company. Dow Chemical Company is only 30 miles away, so we have good relations for that. And these are a series of students who did part of the work. They are all out now in good positions. Tracy Song is a professor at Michigan State University. All the others are in industry except for Eric Ostrander, and he's still working on PhD. So I'm grateful for all their efforts. And as I mentioned before, I'm pleased to be here today, and thank you for showing up.